Hey guys, so the problem we have today basically covers the concept of chemical kinetics, specifically finding the rate law and the rate constant when you're given experimental data. In this case, we have experimental data of two reactants, iodide and peroxo disulfate. We also have their initial rates. Each column denotes a different experiment. That means that when we alter the molarity of one reactant, we want to see the effect that has on their initial rates. We have to use this experimental data to find the rate law and the rate constant. So first, let's find the rate law. Well, the general template for a rate law is that the rate is equal to a rate constant, which we're asked to find in part B, times the first reactant, in this case, iodide, to some power, we'll call it X, times reactant 2, in this case, peroxo disulfate, to some power, in this case, we'll name it Y. When they ask us to find rate law, we need to find what X and Y is equal to. How do we do that? Well, the only way we can do that is by canceling out each reactant one step at a time by comparing different experiments. So let me give you an example. Let's take experiment 1 and experiment 2. If I compare experiment 1 with experiment 2, I want to do it in the form where one of these reactants cancel out. So if I take experiment 1 and compare it to experiment 2, I know that the rate for experiment 1 is 12.5 times 10 to the power of negative 6 moles per liter times seconds. And this is equal to some constant times, well, what is the molarity of iodide in experiment 1? Well, it's 0.080 moles per liter. And we'll write that down. 0.080 moles per liter. And I'll just say M underline for molarity. And that is to some power that we need to find. This is multiplied by the second molarity, 0.040. 0.040 to some power, we'll call it Y. Now let's take the data from experiment 2. And keep in mind I labeled the experiments in red, so for no confusion. So experiment 2, we know that the rate is 6.25 times 10 to the power of negative 6, and that's equal to the molarity of iodide, well, that's equal to a constant, times the molarity of iodide, which in this case is 0.040, to some power, we'll once again call it X, times the second reactant, which is also 0.040, to a Y power, to some power, we'll call it Y. Now, when we, using basic laws of division, we know that the constants will cancel out, and we know that the 0.040s to the Y power will cancel out, meaning that we can solve for X with this given information. So 12.5 times 10 to the negative 6 over 6.25 times 10 to the power of negative 6 is equal to 2. And 0.080 moles per liter to X over 0.040 moles per liter to an X power is equal to 2 to an X power. Now we can use basic logarithmic concepts and ideologies to solve for X. So we can rewrite this as log base 2 to 2 is equal to X. That means 2 to what power is equal to 2? Well, X should equal 1 because 2 to the first power equals 2. So we know that X has to equal 1. So what did we learn from this process? Well, we learned that we have to solve for X and Y one step at a time. So if we want to solve for X, we want to compare two experiments where we can cancel out Y's. Meaning that if we want to solve for X, we have to find an experiment for which the second reactant will cancel out, meaning their molarities have to be the same. In this case, I used experiment 1 and experiment 2 because the molarity of peroxo disulfate is the same, so I can cancel them out when I do the math. I used experiment 1 and experiment 2 also because the molarity of iodide is different. So I can compare the molarities, I can divide the molarities, and I can get 2 to the power of x equals whatever their rates are divided. So 12.5 times 10 to the negative 6 over 6.25 times 10 to the power of negative 6. I can do this, and I can use the laws of division to cancel out the sames, and these would be equal to 1. Same thing, the constants cancel out, and I'm left with 2 to the power of x equals 2, and I can solve for x. So we'll use the same concept, and I will erase our bottom work. We can use the same concept to solve for y. So what 2 experiments will allow me to solve for y? Well, I need to compare 2 experiments where the molarity of our first reactant is the same so that I can compare the molarities for our second reactant. So what 2 experiments allow me to do that? Well, I can take experiment 1 and experiment 3 because the molarity for our first reactant, iodide, are the same, and the molarity for our second reactants, peroxide disulfate, are different. So experiment 1 versus experiment 3. So our rate for experiment 1 is 12.5 times 10 to the power of negative 6 times a constant times the molarity of our first reactant, which is 0.080 to some power, times our second reactant, which is 0.040 to the y power, all over our experiment 3 results. Well, our rate for experiment 3 is 6.25 times 10 to the power of negative 6, which equals some constant, a rate constant, times the molarity of our first reactant, 0.080, times the molarity of our second reactant, 0.020 to y. And we see here that because we picked the 2 experiments in which the molarity for our first reactants cancel out and the constants cancel out, we can solve for y. So 12.5 times 10 to the negative 6 over 6.25 times 10 to the power of negative 6 is equal to 2. And 0.040 divided by 0.020, both to the power of y, is equal to 2 as well, to the y. Once again, using the laws of logarithms, we can find that y is equal to 1 as well. So y is also equal to 1. So when they ask us to solve for a rate law, we can say that the rate is equal to K, which we have to solve in part B, times our first reactant, iodide, to the x power, which we know is 1, so I can put a 1 here, times our second reactant, peroxide disulfate, and we can put S2O8, 2 minus, to the first power, and this will be equal to our rate law. Okay, this is what we need to find for our rate law, finding x and y. For the second part, we'll find our rate constant.